Okay. Uh, Last time we talked about carrier concentration, that is free electrons concentration in the conduction band and free holes concentration in the valence band for an intrinsic semiconductor. And we said an intrinsic semiconductor is a semiconductor which has no impurity, a pure semiconductor. And we found out for a semiconductor like silicon with a band gap of about 1 electron volts, we found out that the carrier concentration, the intrinsic carrier concentration at room temperature, is of the order of 10 to 10 per cubic centimeter. Now, that 10 to 10 electrons per cubic centimeter or 10 to 10 holes per cubic centimeter give us a very, very high resistivity. The resistivity of silicon, intrinsic silicon, at room temperature would be hundreds of kilo ohms, and that is not good enough uh, for a semiconductor in device application. So we have to do something to decrease the resistivity of a semiconductor. In other words, we cannot use an intrinsic semiconductor, so we have to think of something that will decrease the resistivity. And that is why today we'll be talking about the extrinsic semiconductors. And extrinsic semiconductors are opposed to intrinsic, meaning we have some external factors. Okay? These extrinsic semiconductors are sometimes called doped semiconductors. Doped, that means we are adding something foreign or something external to this semiconductor. We have to distinguish between two types of semiconductors, N-type semiconductor, and an N-type semiconductor is a semiconductor which is doped with impurities. Doped meaning we added impurities. And in this semiconductor, instead of having the usual band scheme in a solid, in a doped semiconductor where we added impurities, we will have energy states added to these bands. These energy states are associated with these added impurities. That is to say, the impurities are not part of the semiconductor, and therefore we add them, and hence they produce energy states that are particular to these impurities. So let's start with adding phosphorus. Phosphorus is group 5. We know elemental semiconductors are group 4. So we're going to the neighboring group in the periodic table and picking an element or an atom from that group, adding it intentionally to the semiconductor. So adding an atom from group 5 to an elemental semiconductor, which is group 4. And let's look at a hypothetical two-dimensional semiconductor. Let's be specific. Let's look at silicon. Here is a two-dimensional network of silicon. And you can clearly see a silicon atom, and then you see 4 valence bonds with neighboring silicon atoms. Now let's assume that we've taken away a silicon atom and replaced it by phosphorus. Remember, phosphorus is group 5, silicon is group 4. What does that mean? It means that in silicon we have 4 valence electrons. In phosphorus we have 5 valence electrons. Okay? So what happens the phosphorus has 5 electrons and it replaces silicon. You see here, silicon has gone, and instead of silicon, we have phosphorus. So 4 of the valence electrons for phosphorus will share bonds with the neighboring silicon atoms. But we know that phosphorus has 5 electrons. So 4 of them share valence bonds or covalent bonds. And then this 5th electron is not needed anymore. And it becomes very unstable. And therefore, it is better for this 5th electron to set itself free from the phosphorus atom and becomes a free electron. So the 5th electron becomes a free electron. And again, here we have another phosphorus atom. 4 of its electrons are engaged in covalent bonding. And then the 5th electron becomes free. And here is another phosphorus atom, and the 5th electron becomes free. So these 3 phosphorus atoms have given us 3 free electrons. So this phosphorus atom is called a donor. A donor is somebody who gives. So the phosphorus atom has given us 1 free electron. That is why it's called a donor atom. And the process by which phosphorus atom is added to silicon is called doping. So we have doped this silicon with phosphorus atoms. And each phosphorus atom has donated a free electron. So each phosphorus atom is a donor. What we have here is number of added free electrons. There are no free holes generated, no free holes, just free electrons. Electrons are negatively charged. So this semiconductor, we have increased the number of free electrons, the negative charge, and therefore we call it N-type, negative type, N-type semiconductor. In an N-type semiconductor, I have free electrons, more free electrons. And these free electrons at room temperature are exactly equal to the number of added phosphorus atoms. So if I add 10 to 15 phosphorus atoms per cubic centimeter, then I have added 10 to 15 free electrons per cubic centimeter. That is to say, my N in this material becomes 10 to 15 per cubic centimeters. So this is 5 times larger than the intrinsic silicon, where in the intrinsic silicon you have Ni, which is the intrinsic carrier concentration, which is the free electrons and free holes of the order of 10 to 10. So you have increased the number of free carriers by 5 orders of magnitude. That is to say, you have decreased the resistivity by almost 5 orders of magnitude. That is to say, in an intrinsic silicon, where the resistivity was hundreds of kilo ohms, you have now reduced it to a few ohms. You have reduced the resistivity. And this material is called N-type because the conduction is by electrons which are negatively charged. So this is how you make an N-type semiconductor. It's extrinsic because you have extrinsic atoms added, and these extrinsic atoms are the phosphorus atoms. So this is how you create an N-type, an extrinsic N-type semiconductor, and this is a highly conductive semiconductor. So in summary, When you add phosphorus atoms, they will share 4 of their electrons with the 4 neighboring silicon atoms, making bonds. The fifth valence electron is very unstable, becomes very unstable, and it therefore can be freed from the phosphorus atom, and it becomes a free electron. This fifth electron is bound with this energy, is tied to the uh, atom with this energy, which is very, very small, which is the energy of the atomic shell. This energy is very small, very, very much less than the band gap. Indeed, it is of the order of 0.04 electron volts. So this is a very, very small energy compared to the band gap. Remember, the band gap in silicon is 1.2 electron volts. So to make a free electron in silicon, that is to excite an electron across the band gap, you need 1.2 electron volts. But to make this electron in a donor, in a phosphorus atom, free, you only need 0.04 electron volts, much, much smaller energy. Therefore, you can readily have the phosphorus atom donating its electron to the conduction band, becoming a free electron. So this is the energy of the electron that needs to become a free electron, and as we said above, there is 0.04 electron volts. So this is a very small energy, and therefore, once you put the phosphorus atom in the silicon crystal, it immediately gives away its electron at room temperature, and the electron becomes a free electron. Also, the number of free electrons per unit volume is equal to the number of donors, which I call them capital N with subscript D. That is the number of donors or phosphorus atoms per cubic centimeter that we put in the crystal. That's exactly equal to the number of free electrons. One thing that I want to point out is that in a silicon crystal, we said you have 10 to 23 atoms, silicon atoms per cubic centimeter. Okay? And now you can add phosphorus atoms of the order of 10 to 15 or 10 to 16, right? To increase the conduction. You can see that 10 to 15 is very much less than the total number of atoms per cubic centimeter in phosphorus, which is 10 to 23. That is to say, in every one donor atom, there are 10 to power 8 silicon atoms, right? So one atom in 100 million atoms of silicon is replaced by phosphorus. So that is very small. That is like replacing 1 in 100 million. 1 in 100 million is a very small. So the silicon will not change. Its color will not change. Its properties, mechanical properties will not change. But we see that the conductivity changed quite a bit, 5 orders of magnitude from intrinsic silicon. So the resistivity changes from hundreds of kilo ohms down to a few kilo ohms. So no much change in silicon as a material, but much change in the electrical properties. So this is how we make an N-type semiconductor. Okay, so this phosphorus atom gives away its electron and it becomes positive, becomes ionized. So the phosphorus atom is called donor atom. So all atoms with 5 valence electrons, we don't have to have just phosphorus atom. Any atom with 5 electrons. Any atom from group 5 can be a donor in silicon. So you have atoms like antimony, you have atoms like uh, arsenic, as well as phosphorus. All of those can act as donors. So atoms with 5 valence electrons are in group 5 of the periodic table, and they're all donors. These atoms will donate electrons if they substitute the host atom, which is silicon in this case, which is group 5 in the elemental semiconductor, and therefore it makes the semiconductor n-type. As I told you, these atoms, these donor atoms, need very little energy, 0.045 electron volts, which is very small compared to the band gap, which is 1.2 electron volts or so, to become free. And therefore, readily the semiconductor becomes n-type with an enormous concentration of electrons compared to an intrinsic semiconductor. And its resistivity now is very small compared to the resistivity of the intrinsic semiconductor. However, you immediately see something very interesting. By changing the number of donors, the concentration of donors per cubic centimeter, we are changing n, the concentration of free electrons, and therefore we're changing the resistivity of, of the material. So we are engineering the resistivity. So here we have a material, and by adding impurities in a controlled concentration, we're changing the resistivity of this material. So we have an engineered material, a material that we can engineer. Of course, we cannot do this in metals. Metals have one fixed resistivity, which we cannot change. We cannot do this with insulators. Insulators have a very high resistivity, which we cannot change. But you can see here in a semiconductor, you can change the resistivity from hundreds of kilo ohms, maybe mega ohms, centimeter, down to a resistivity of uh, uh, from a resistance of hundreds of kilo ohms or mega ohms down to a resistance of uh, few ohms. So we can engineer a semiconductor to change the resistance by so much. So now, as I said, if we add phosphorus atoms to a concentration on 10 to 15, then we have 10 to 15 electrons in the conduction band, or free electrons. So we have 10 to 15 of them. And therefore, we have a resistance that is decreased. Remember, for an intrinsic semiconductor, we have 10 to 10 per cubic centimeter. So we have increased the concentration of free electrons by 5 orders of magnitude. So that means we have reduced the resistance by 5 orders of magnitude. And again, as I argued, in a crystal, you have 10 to 22 to 10 to 23 atoms per cubic centimeter, and you have only added 10 to 15 atoms per cubic centimeters. So it is 1 in 10 to 7 or 10 to 8 atoms added by, 1 atom of phosphorus replaces, a phosphorus atom replaces 1 silicon atom in 10 to 7 to 10 to 18 atoms. So obviously nothing happens, by way of changing silicon characteristics, except that the electrical conductivity or the electrical resistance or the electrical properties are hugely changed by quite a bit. Again, this balance equation, remember we drive this equation back in the beginning, in the beginning of this chapter, and it simply says the concentration of free electrons in a semiconductor times the concentration of free holes in a semiconductor equals the square of the intrinsic concentration. The intrinsic concentration is that concentration in an intrinsic semiconductor. Now, let's take silicon for instance. If we dope silicon with 10 to 15 donors, then we make N 10 to 15. And we know Ni in silicon is 10 to 10. So if we substitute 10 to 10 here, and if we substitute 10 to 15 here, then we get P of the order of 10 to 5. So the concentration of free electrons is huge, 10 to 15. The concentration of free holes is very small, 10 to 5. The difference between the two is about 10 orders of magnitude. So this semiconductor is dominated by electrons or the negative charge, and therefore it's called the N-type semiconductor or the N-type silicon. Similarly, the N-type indicates that the charge carriers are the negatively charged electrons. So the example discussed above was specific to silicon doped with phosphorus. But we can dope silicon with any member of group 5 elements. They could be arsenic, they could be any other group 5 element, and we can dope any elemental semiconductor. It doesn't have to be silicon. It could be germanium, which is group 4. We can still dope it with a member of group 5 to make it N-type. So how do we express this in an energy diagram? For an N-type, for a semiconductor, we know we have a conduction band, we have the valence band, and we have the band gap between the conduction and the valence gap and the valence band. We also know that in an intrinsic semiconductor, the Fermi level is almost in the middle, near mid-gap. EI is mid-gap, and the Fermi level is pretty much near the middle of the gap. However, when we put donors, that is phosphorus, say in silicon, they have an energy state associated with these donors, and therefore we show these energy states schematically as part of the band diagram. We show the donor state of phosphorus as an energy state such that the difference between the bottom of the conduction band and this state here